Okay, in this video we're going to look at Lagrange's method based on chapter 2 of Dixit, pages 17 to 19, with an example provided on page 19 to 20. Although Dixit doesn't start this way, the problem we're interested in solving is a constrained optimization problem. We wish to, 1, maximize utility subject to a budget constraint, or alternatively minimize the cost of producing and achieving a certain level of output, which is the production problem. Consider the more general problem where we're maximizing some objective function f of x subject to g of x equals c. Now, the f of x and the g of x can be linear or nonlinear, and we'll look at that in terms of concavity and convexity in another lecture. We form the Lagrangian function as follows. We define the Lagrangian as a function of x and this lambda, which we call the Lagrange multiplier. And we set up the Lagrangian by first putting the objective function here and then adding lambda, the Lagrange multiplier, times the right-hand side of the constraint minus the left-hand side of the constraint, or the constraint function. This is the exact equation that Dixit derives, and it's numbered 210. Note how we write that constraint, because we can also write it as lambda being a negative number here, with the left-hand side of the constraint subtract the right-hand side of the constraint, but then we have to have that negative there. So we're going to be using this form, number 1, throughout most of our discussions concerning Lagrangians, unless I indicate otherwise. So recall that we write a vector x. So we've been doing this like this, and this is a column vector consisting of x1 and x2. X and lambda are unknowns, so we have 3 unknowns that we have to solve for, x1, x2, and this lambda. To do so, we set the first partial derivatives of the Lagrangian function equal to 0 and solve the resulting equations for x1, x2, and lambda. And here's how that looks. So this is the partial derivative of the Lagrangian with respect to x1, the partial of the objective function with respect to x1 minus lambda times the partial of the constraint function with respect to x1. We do exactly the same thing for x2, so we get the partial of the Lagrangian with respect to x2. This is the partial of the objective function with respect to x2, and the partial of the objective or the constraint function with respect to x2 multiplied by lambda. And notice that there's that negative in front of each, and the reason for that is the way we wrote this negative here. All right, the same thing would occur if we use this functional form. We'd have the negative here, however. And finally, the third constraint is simply that the partial derivative of the Lagrangian with respect to lambda is c minus g of x, set it equal to 0, and we just get the original constraint back, which is almost always the case. Well, it is always the case if we do this for the lambda. So the approach to solving this, in this case, is first to solve 1 and 2. For, if we look at 1, we solve it for f1 over g1 being equal to lambda, and for the second partial derivative set to 0, we get f2 over g2. Remember, these are partial derivatives with respect to x2, and this one with respect to x1. So this gives us the result that f1 over g1 equals f2 over g2, simply setting this and this equal because both sides are lambda. And we can rearrange this so that we get the ratio of f1 over f2 equal the ratio of g1 over g2 in optimality. And this gives us back These results are found back in chapter 1 of Dixit. So let's draw upon the example of Dixit on pages 19 and 20. So we have a utility function. In this case, utility is a function of x and y rather than q1 and q2. I'm trying to make it a bit easier to just work through. And we get a Cobb-Douglas utility functional form. Now we can do a monotonic transformation of this so that the utility function, the new utility function, is written as alpha log of x plus beta log of y plus this log of a, but a is just a constant, and we'll see that it just falls out in the when we take first derivatives. And we have the budget constraint, p of x times x plus p of y times y is equal to our m, our budget. Our objective is to maximize utility, maximize this utility function, subject to the budget constraint, and we then form the Lagrangian. Lagrangian is a function of x, y, and lambda, and it's given by the objective function, which is the utility function, plus lambda times m, that's the right-hand side of the constraint, minus p of x times x minus p of y times y. Take the first derivatives, and we get the marginal utility of x minus lambda times the price of x equals 0, and the marginal utility of y minus lambda py equal to 0. And we solve both for lambda and set them equal to each other because they're both equal to lambda. And we get the marginal utility over the price of x equal to the marginal utility of y over the price of y. Now, what we find is the marginal utility of x is equal to the first derivative of this right-hand side. Well, this we've already said falls out. X does not appear in this part, so log of x is simply 1 over x, so we have the marginal utility is alpha over x. And the same thing with marginal utility of y is beta over y. So keep that in mind. And when we take the derivative, the partial of the Lagrangian with respect to lambda, we end up with our budget constraint again. So what we do is we first find these marginal utilities of x, lambda alpha over x, and we can solve that for x by first arranging it. And so what we do is we look at we put this back into the budget constraint, and we get, well, pardon me, we don't even do that. We plug in this value of alpha over x here, and we have that over here, and that's equal to lambda, and then we just rearrange it so that alpha over x equals lambda times px. We move this px over to that side. So u of x is equal to lambda px. This is u of x, lambda px, and we solve for x, and we get alpha over lambda times p of x. And the same thing, if we do that with y, then we get y equals beta over lambda times the price of y. Then we substitute x and y into the budget constraint. So we take that value, plug it into that x, this value, plug it into that y, and we get for the x this one, for the y this one, which is equal to, because the px cancels px and py, alpha over lambda plus beta over lambda equals m. Solve for lambda. All right, we multiply through by alpha, and we get alpha plus beta equals lambda m. And solve for lambda, we find that it's equal to alpha plus beta over m. And because these are the same for y and x, we get this for both of them. So we solve for the x and the y, and we get the result that alpha over lambda p of x. All right. So we solve the budget constraint for that, we get alpha over alpha plus beta m. Okay, we're substituting that alpha here, and that's equal to alpha over m, alpha plus beta times p of x. So that x is a function of p of x and m. Notice that the price of y does not come in here. It just does not come in. Likewise, we solve for y rather, and we get beta m divided by alpha plus beta, all multiplied by the price of y. And again, y is a function only of p of y and m, not of the price of x. So it tells you right away that the two are totally separate, that only income and the p of y matter in the case of y, and only income and p of x in the case of x. So let's consider budget shares and define the budget share as XS, and that's simply the amount of x times the price of x over the total budget, which when we plug in these values from up above, we end up with alpha divided by alpha plus beta. The budget share for y is equal to y times p of y over m, and that turns out to be beta over alpha plus beta. So the result here is that the share of income spent on the two commodities remains constant regardless of changes in income or prices, which is probably a little unrealistic. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.